Good morning, students. Now, today, that is part 11 of the video lecture in continuation with the video lectures for mechanical properties of fluid. Today, we are going to discuss about viscosity. So, viscosity means what? Let us discuss about the term viscosity. And as you had seen that, suppose there is a solid of mass m and it is moving with velocity v on a rough surface. If it is a rough surface, on a rough surface, a body of mass m is moving with velocity v, then there is a force, that is opposing force, that is called as the frictional force, acts between the body and the surface. This opposes the velocity of the object. Similarly, there is, suppose fluid is flowing in a tube, a fluid is flowing, then in between the layers, suppose this is layer 1 and layer 2. So a force which opposes, that is called as viscous force. Viscous force. This force is called as viscous force, which opposes the motion of layers inside the tube, and this viscous force is the opposing force, and so it is called as the viscous force, and it opposes the motion of the liquid layers, and the property which arises is called as viscosity. So the tendency of the fluid to oppose the relative motion of its layers, tendency tendency of fluid to oppose the relative motion between the layers is called viscosity, is called viscosity. That tendency or that property which opposes the relative motion between the layers is called as viscosity, and the backward dragging force is called viscous force or viscous drag. Backward dragging force, backward dragging dragging force is called viscous force, viscous force or viscous drag. Viscous, that is called as viscous force or viscous drag. Now we will find the coefficient of viscosity. Coefficient of viscosity. So for understanding the coefficient of viscosity, first of all, let us assume that this is a pipe, and in this pipe the fluid is flowing. Suppose this is the axis of the pipe. This is the axis of the pipe. And in case of laminar flow, we had seen that the maximum velocity of the layer is along the axis of the pipe, and subsequently the velocity of the fluid decreases, and at this point the velocity becomes zero. The velocity becomes zero. So what we will observe, we observe that, suppose this thing will take place. Okay, and if it is L, this length is L, and the liquid layers are flowing like this. Liquid layers are flowing like this. So if it is L, then what will happen? If delta L is the distance moved, delta L, delta L, that is, if the fluid is flowing with velocity v, if the fluid is flowing with velocity v, then v into delta t, v into delta t is the distance moved by the fluid, and v into delta t, v into delta t is called as delta L. So look at here, this is just like a shear strain, this is just like shear strain, and the shear stress is applied over here. So the here we can apply that shear strain, shear strain, shear strain can be written as delta L upon L, and shear stress is what? Shear stress equal to force upon area. So dear students, force upon area. So the coefficient of viscosity, the rate of change of strain, we first of all we find the rate of change of strain, rate of change of strain, and rate of change of strain is what? Delta L upon L divided by delta T, and it can be written as delta L delta T, and it is equal to V upon T. So V upon L, delta L upon delta T is V, and it is equal to V upon L, because we can replace it as delta L upon delta T can be replaced by what? It can be replaced by V. So coefficient of viscosity is defined as rate of shearing stress to shearing strain. So it can be defined as what? Coefficient of viscosity, coefficient of viscosity is defined as the ratio of shearing stress to the strain rate, shearing stress to the strain rate. And so coefficient of viscosity can be defined as F shearing stress upon strain rate. And shearing stress is what? Shearing stress is equal to F upon A upon shearing strain rate is what? Delta L upon L divided by delta T, and it can be written as F upon A upon V upon L, and it can be written as FLA into V, FLA into V. So we can write it as coefficient of viscosity can be written as F upon A divided by dv upon dx. dv upon dx means if the velocity is changing along x direction, if the velocity is changing along x direction, then this is dv upon dx is called as velocity gradient. Velocity gradient. This is called as velocity gradient. So it can also be said that eta is the ratio of shearing stress upon velocity velocity gradient. Shearing stress upon velocity gradient. If the velocity is changing along x direction, then it can be written as f upon a divided by dv upon dx. If velocity is changing along y direction, then it can be f upon a dv upon dy. If along z direction, then f upon a upon dv upon dz. So this is about the definition of coefficient of viscosity. Now we will discuss about its dimensional formula and its unit. Now dear students, dimensional formula dimensional formula for eta. We have to discuss about the dimensional formula for eta, and as you know that eta is equal to what? F upon a v upon L, or you can say that F into L a into v. Now look at here, force mlt minus 2 L upon L square into lt minus 1, and it can be written as m L square t minus 2 upon L cube t minus 1, and it can be written as m L minus 1 t minus 1. So dimensional formula for coefficient of viscosity, it can be given as m L minus 1 t minus 1. Now dear students, we have to discuss about the units of viscosity. Unit of viscosity. Unit of viscosity. What is the unit of viscosity? So first we will discuss about SI unit of viscosity. SI unit of viscosity. So SI unit of viscosity is Poiseuille. One Poiseuille. One Poiseuille, and one Poiseuille can be written as 1 Newton upon 1 meter square into 1 meter into 1 meter per second. Okay, and it is equal to what? Look at here, meter to meter cancel out, and it is equal to 1 Newton second per meter square. 1 Newton second per meter square, or kg meter per second. 1 kg per meter second. 1 kg per meter second, or it is called as 1 decapoise. 1 decapoise. This is SI unit of viscosity. So the coefficient of viscosity of a liquid is said to be 1 Poiseuille or 1 decapoise if tangential force of 1 Newton meter square of surface is required to maintain the relative velocity of 1 meter per second between the layers of the liquid which is 1 meter apart. Clear? Now second one is CGS unit. CGS unit of viscosity. CGS unit of viscosity, and CGS unit of viscosity is poise. 1 poise. And this is equal to 1 dyne 1 centimeter square into 1 centimeter upon 1 centimeter per second, and it can be written as 1 dyne second upon centimeter square, or it can be written as 1 gram per centimeter second. It can be written as 1 gram per centimeter second. This is the CGS unit of viscosity. This is CGS unit of visco, 1 dyne second per centimeter square. So the relation between what? Decapoise and poise. Relation between decapoise and poise, and it can be said that one poisely or one decapoise is equal to 10 poise. This is the relation between CGS and SI unit of viscosity. So 1 poisely or 1 decapoise is equal to 10 poise, and viscosity, as viscosity does not have any direction, so it is a scalar quantity, and so we can say that viscosity coefficient of viscosity is a scalar quantity. Coefficient of viscosity is a scalar quantity. Okay, students, this is about the coefficient of viscosity, and it is a scalar quantity. Now moving towards the relative viscosity. Now dear students, relative viscosity. Relative viscosity. Since it is given that relative viscosity means it is the ratio of two viscosities. So relative viscosity of a liquid is the ratio of viscosity of the liquid with respect to water, viscosity of water. So relative viscosity of a liquid, it is equal to viscosity of liquid to the viscosity of water. Relative viscosity is the ratio of viscosity of the liquid to the viscosity of water, and it can be eta liquid to the eta water. Viscosity of the liquid to the viscosity of water. So dear students, relative viscosity of blood remains constant between 0 degrees to 37 degrees Celsius. Means between this temperature, that is 0 degrees Celsius to 37 degrees Celsius, if we compare the viscosity of blood with the relative viscosity of the blood with the viscosity of water, then its value is always constant. Now, effect of temperature on viscosity. Effect of temperature on viscosity. Effect of temperature on viscosity. The first thing is that the viscosity of liquid decreases with increase in temperature. Viscosity of liquid, viscosity of liquid decreases decreases with increase in temperature. Viscosity of liquid decreases with increase in temperature, that is viscosity of liquid is inversely proportional to 1 by absolute temperature. And the second thing is viscosity viscosity of gases increases with increase in temperature. Increase in temperature, that is, if we say that viscosity of gas is directly proportional to under root T, means as the temperature is going to be increased, the viscosity of gas is going to be increased, because in case of gases, the gas molecules are in their random motion, and with increase in temperature, the internal energy of gases is kinetic energy of gases is going to be increased, due to which the random motion increases, and so we can say that the viscosity of gases increases with temperature, while in case of liquid, it happens that the viscosity, yeah, as the temperature increases, due to increase in temperature, certain liquid vaporizes, changes into gases, and the density of the liquid decreases, due to which its viscosity decreases with increase in temperature. So these are the two things which we can see, that the effect of temperature, these two things have no any experiment mathematical proof. Experimentally it has been observed, and the direct results it is given here. Now, dear students, we will discuss about critical velocity. Next discussion is critical velocity. Critical velocity. So, dear students, critical velocity is nothing. Critical velocity is that limiting value of velocity of a fluid up to which the flow of the fluid is streamlined, and after that it becomes turbulent. So, it is the limiting value limiting value of velocity of a fluid up to which the flow of the fluid is streamlined streamline and above which the flow becomes turbulent above which the flow becomes turbulent. So that limiting value of velocity up to which the flow is streamlined, that limiting value of velocity is called as critical velocity, and above this value of the velocity, the flow of the fluid becomes turbulent. So that type of velocity is called as critical velocity. Now we are going to find out the value of the critical velocity. So experimentally it was observed experimentally it was observed that experimentally it was observed that the critical velocity of the fluid depends upon depends upon following factors depends upon following factors. On what factors the critical velocity of the fluid depends? That is, first one is the coefficient of viscosity. Coefficient of viscosity, that is equal to eta. The second thing, it will depend on the density of the liquid. Density of the liquid, that is equal to rho. And third one is radius of the tube. Radius of the tube, that is equal to r. So on these three factors, the critical velocity, the value of critical velocity depends on these three factors. Now you had studied in case of applications of dimensional analysis, application of dimensional analysis, application of dimensional analysis. In application of dimensional analysis, you had studied that the three things we used to do. First one is uh, checking the consistency of any dimensional equation or any physical equation which is given. The consistency of that physical equation can be done on the basis of dimensional analysis. Second one is conversion of one unit into another unit. And the third application is deriving the formula. Means, if suppose it is given that the time period of the simple pendulum depends upon the length of the bob and the acceleration due to gravity, these things it is given, then you can find out the relation for the time period of the simple pendulum. Similarly, here also the critical velocity depends upon these three factors. So by the help of dimensional analysis, we can find out the expression for the critical velocity. So look at here how to find out the how to find out the expression for critical velocity. So here it is given that critical velocity C is directly proportional to the coefficient of viscosity. It is directly proportional to the rho, and it is directly proportional to eta. So we can say that Vc is directly proportional to eta rho r. And from here we can say that Vc is equal to K eta A rho B and R C. Clear? Now dimensionally we can write it as Vc is equal to m 0 L T minus 1, that is equal to K eta m L minus 1 T minus 1 power A rho L that is m L minus 3 power B and L power C. And from here we can write it as m0 L T minus 1 and K m power A L power minus A T power minus A, m power B L power minus 3B, and third one is L power C. Clearly, so we can write it as m0 L T minus 1 K m power a plus b. Base are same, so exponents are added. L minus a minus 3b plus c and t minus a. These things we had written. Now, dear students, on comparing the powers, on comparing the powers, on comparing the powers, we can get what? A plus b is equal to 0. Then minus a minus 3b plus c, that is equal to 1, and minus a is equal to minus 1. And from here we can get a is equal to 1, b is equal to minus 1, and c is equal to what? C is equal to also equal to minus 1. C is equal to minus 1. On solving this we will get, and putting the values here, Vc is equal to k eta power 1, rho power minus 1, and r power minus 1. And from here we will get the value Vc is equal to k into eta upon rho r. Vc is equal to k into eta upon rho r. So for the flow to be a streamline, value of Vc should be large. For flow to be streamlined, value of Vc should be large. Value of Vc should be large. And for the value of Vc should be large, what the conditions? N should be large, that is eta should be large, and rho and r should be small. Okay, means since Vc is directly proportional to eta, so as eta is greater, Vc will be greater, and for Vc will be greater, these two things, that is density and radius of the tube, should be smaller. So this is the expression for critical velocity. Now, dear students, we are going to discuss the next topic, that is Stokes law. Okay, dear students, next heading is Stokes law. Stokes law. And what is Stokes law? English physicist Sir George G. Stokes, English physicist. He was the English physicist Sir George G. Stokes, and he had observed that by performing various experiments on the fluids, he had observed that suppose there is a container, and in this container fluid is kept. So he had observed that if a spherical ball is dipped inside that liquid, then the backward dragging force, there is a backward dragging force which is applicable on the ball, is due to the layers of the liquid. That backward dragging force is due to the liquid layers, and that backward dragging force is directly proportional to the viscosity, that F, that backward dragging force, this backward dragging force is directly proportional to eta, is directly proportional to R, and is directly proportional to V. Eta is the coefficient of viscosity, visco coefficient of viscosity of the fluid. R is the radius of the bob or a spherical ball what, and V is the velocity, and V is the velocity. So the smallest spherical body of radius r moving through fluid, so that dragging force, we have to find out the value of that dragging force. What is the value of that dragging force? So this this dragging force can be calculated similarly on the basis of the dimensional analysis, and here we can say that F dragging is directly eta r v, and you can say that it is equal to k eta to the power a, r to the power b, and v to the power c. Now look at here, it can be written as mlt minus 2. The force is given as mlt minus 2, and this is equal to k m l minus 1 t minus 1 power a, l power b, and l t minus 1 power c. And from here we can write it as m l t minus 2, it is equal to k m power a, l power minus a, t power minus a, l power b, l power c, t power minus c. And it can be written as m l t minus 2 k m power a, l power minus a plus b plus c, and t power minus a minus c. On comparing the powers, we get what? A is equal to 1 minus a plus b plus c is equal to 1, and minus a minus c is equal to minus 2. So from here we get minus 1 minus c is equal to minus 2, and from here we get minus c is equal to minus 2 plus 1, or minus c is equal to minus 1, or c is equal to 1. So a is equal to 1, c is equal to 1, and then minus 1 plus b plus 1 is equal to 1, and from here b is equal to 1. These two cancel out and b is equal to 1. So we had get the value a is equal to 1, b is equal to 1, and c is equal to 1. These three values we had got, and putting the value in equation 1, putting values in equation first. So what we get? We get F dragging is equal to F dragging, that is equal to k eta r v, and experimentally it was observed that experimentally k, the value of k will be 6 pi. So F dragging that is equal to 6 pi eta r v. F dragging is equal to 6 pi eta rv, and this f dragging equal to 6 pi eta rv. This is called as Stokes law. This is called as Stokes law. Now, dear students, our next discussion is terminal velocity. Terminal velocity. This terminal velocity can be denoted as Vt. This is terminal velocity. So let us understand what is terminal velocity. Suppose it is a container. It is given that this is a container, and in this container there is a liquid. There is a liquid filled in this container. Suppose there is a liquid in this container. Now, dear students, suppose a small spherical ball of radius r is dipped inside it. So what are the forces acting? There is the weight of the spherical ball, weight of the spherical ball, which is acting downward direction. In upward direction, upthrust is acting in the upward direction, and similarly there is what we had studied in the Stokes law, a dragging force, that is f dragging force. These three forces supposed to be act on this body. Now suppose the liquid is moving with velocity v inside the fluid, then there is a stage comes when the weight of the liquid is balanced by the dragging force and upthrust. And what will happen at that time? At that time, the spherical ball starts moving with constant velocity. Means if f dragging plus upthrust is equal to weight of the this is equal to weight of the spherical ball, then if this condition is satisfied, then a spherical ball starts moving with constant velocity, and this constant velocity with which the spherical ball starts moving under the effect of these forces, this constant velocity is called as terminal velocity. This constant velocity is called as terminal velocity. So we are interested to find out the expression for the terminal velocity. So for this, suppose the density of liquid is sigma. Sigma is the density of the liquid, and rho is the density of a spherical ball. Rho is the density of a spherical ball, and sigma is the density of the liquid. So look at here, what is the value of this? The upthrust. First of all, we are finding the upthrust. And what is the value of upthrust? Upthrust is equal to what? Upthrust is equal to the buoyant force. since upthrust is equal to buoyant force, and as you know that the buoyant force acting on the spherical ball is equal to the weight of the liquid displaced by the spherical ball. So the weight of the liquid displaced by the spherical ball, so it can be given as 4 by 3 pi r cube. This is the volume into density of the liquid sigma into g. This is equal to upthrust. Now F dragging, this is equal to 6 pi eta r v. This is the value of F dragging, and weight of the spherical ball. Weight of the spherical ball is 4 by 3 pi r cube sigma into g. Okay. Now equating all this, so 4 by 3 pi r cube sigma into g plus 6 pi eta rvt, that is terminal velocity, is equal to 4 by 3 pi r cube rho g. And from here we want to find out the value of terminal velocity, so it can be written as 6 pi eta rvt is equal to 4 by 3 pi r cube rho g minus 4 by 3 pi r cube sigma g, and it can be written as 6 pi eta rvt equal to 4 by 3 pi r cube g rho minus sigma. Okay, and from here we can write it as Vt is equal to 4 by 3 pi r cube g rho minus sigma upon 6 pi eta r. Okay students, now pi to pi cancel out, r to 1r, it becomes r square. So Vt is equal to what? 2 by 9 into r square g rho minus sigma upon eta. So terminal velocity can be given as what? 2 by 9 r square g rho minus sigma upon eta. This is the terminal velocity. So what you are seeing, that terminal velocity is directly proportional to the square of the radius of the spherical ball. So dear students, this is all about the terminal velocity. Now this is all about the chapter, that is fluid mechanics chapter 10. Now in the next video we will start our next chapter, that is thermostatics or thermal properties of matter. Okay, thank you students, have a nice day.